we're going to graph the other two derivatives based on that. So we're going to take that function and get the first derivative. So y prime, this is still 3.4. Bring your 3 down. What happens when you do 1/3 times 3? Good. And then we're going to have x squared minus 1. Okay, so I'm going to graph that. That's a parabola. That's down 1. This is y equals 1/3 x cubed minus x. Okay, now, let's think back to your first derivative test back in section 3.3. It told you about when the original was increasing or decreasing. Okay, so let's look at the green graph. The green graph is your derivative. This whole part of the green graph is positive, and by that I mean that it's above the x-axis. So in this section, what's the original doing when the derivative is positive? Increasing. Okay, now, this whole section of your derivative is below the x-axis, so it's negative. What's your original doing? And then this part is switching on us. So then we're going to go opposite of that. Okay, now, let me add in our second derivative. Let's go purple. What's the derivative of x squared minus 1? Okay, so that is this line. Okay, now, we can apply the first derivative test with this. This purple line is the derivative of the green line. The purple line is negative in this whole section, so what's the green line doing? Okay, purple line is positive, green line is increasing. Okay, so that was what section 3.3 was all about. And the reason why I review that is it's coming back today a little bit. Then we got to section 3.4, and we did the test for concavity. Okay, so what that tells us is when the second derivative is negative, the original is concave down. When the second derivative is positive, above the x-axis, the original is concave up. What happened right here? What do we call that point? Where the concavity changes. Point of inflection. And what's happening with the second derivative? It's crossing over the x-axis at that point. So that's what the test for concavity did. So we're going to bring that back here in just a little bit. But that's conceptually what's been going on. We've done 2 tests. The first derivative test and the test for concavity. Today, maybe, we're going to do the second derivative test, is what we're going to learn. So I'm going to let you copy down that stuff, and then I'm going to explain it to you. And if you're going to get annoyed with any test, it's going to be this test. And once you're writing it, you might figure out why you're going to get annoyed with this test. Some of you already know. It works.
Like 40%. Like 1 in 100.
No, not that small. 2 out of 3. Maybe. And this is going to bring on another chart. And this chart's going to be different than the other 2. It's going to look a little bit different. But we'll be learning this new chart. And I think the name is stupid because you're not just using the second derivative, you're using the first derivative. So whoever named this, I disagree. Okay, what can you tell me about critical numbers? What do you remember about them from section 3.3 or 3.1? How do you find that? Let's start there. Good. So figure out what your derivative is, set it equal to 0. What if you have a fraction for your derivative? Top and bottom, because it could be where it equals 0 or where it doesn't exist. So that's what this is telling us to do first. Get our first derivative, figure out where it equals 0 or does not exist. What do critical numbers indicate is my second question. Maxes or mins? Do they have to be maxes or mins? No, they could be fake outs. Well, they relative or absolute, yes, but then they wouldn't have to necessarily be that. They could fake you out. Let me give you an example of a fake out, just with a graph. If we would take the graph of x cubed, the math would tell us that there's a critical number there. Is that a max or a min, though? No. So critical numbers could be mins or maxes, but they don't have to be. So that's what we're going to figure out. Okay, now, here's where the second derivative test comes into play. We're going to get our critical numbers, where there could be mins or maxes, and we're going to take that critical number, and we're going to put it in the second derivative. And second derivative tells us if it's concave up or concave down. So if we put this number into the second derivative, and it tells us it's concave up, is that a min or a max then? A min. If we put it into the second derivative and it tells us at that point it's concave down, that's going to be a max. So that's what the idea behind second derivative test is. This line, however, comes into play that there are going to be multiple fake outs that tell you, this test just isn't good enough. We've got to rely on another test. So there is the possibility that the test won't work, and we'll have to go back to first derivative test, because first derivative test told us mins or maxes. Okay, so let's go through an example, and we'll work through one slowly to see how this is run. And here's what the directions are going to look like. Find the extrema of f of x equals negative 3x to the fifth plus 5x cubed using the second derivative test. Okay, now, if we didn't have using the second derivative test up there, and it just said find the extrema, do you know how else you can find the extrema? Derive, solve for x, plug those into the first derivative test. Because remember, the first derivative test, if it changed from increasing to decreasing or decreasing to increasing, it told you mins or maxes. And that's probably going to be your go-to method. So there's going to be these directions when, like, the book homework is forcing you to use the second derivative test, or like on your quiz when I'm going to force you to use the second derivative test, I will put that in the directions. Okay, so let's work through this. First part of the directions say find the critical numbers. So that means find your first derivative, set it equal to 0. So f prime of x equals negative 15x to the fourth plus 15x squared. That's our first derivative of the function. Factor out what, Nick? 15x squared we can factor out. Okay, then that's going to leave us with negative x squared plus 1. Set that equal to 0. So set each part equal to 0. Here, divide by 15, square root, x equals 0. Here you can add x squared to each side, so you have 1 equals x squared. Square each side, what do you get for your critical number? Good. Okay. Is there any spot where this is going to not exist? No. Those are polynomials. They're going to work. So we've got 3 critical numbers. Okay, now we're going to take those, put them in our chart. Okay, now our chart is only 3 rows in this, and you have a column for each critical number. We're not going to do intervals on this one. So I'm going to have my 3 columns for each of the critical numbers, and then my title column. And here's what the title column is going to be. Critical numbers, sign of second derivative, and extrema. So this chart is different than the other 2. The other 2 are very similar. This one's different. And then we put our critical numbers in the top row, no intervals, and put them in order from least to greatest. So we're going to have x equals -1, x equals 0, and x equals 1. So those are possibilities of high and low points. They might be fake outs, but they could be the higher low points. Okay, now, the next part of our directions say, use the second derivative to figure out if they're a min or a max. So that means we need to find the second derivative. So I'm going to take my first derivative, and I'm going to take it in its easiest form, and I'm going to derive it again. So I'm going to say the second derivative of this is -60x cubed plus 30x. And then I plug each of those critical numbers in there. Now this says sign, so that means I only need to know if they're positive or negative. I don't really need to know what number exactly it is. So I just need to plug that number in. If I plug a -1 in, this is going to end up being -1 times -60, which is 60 minus 30. So that's positive. So if I put a 0 in there, if I put a 1 in there, it's going to be -60 plus 30. Okay. All right, so this is telling us something about our second derivative. When our second derivative is positive, that means it's concave up. So what kind of extrema is that? A min. Let's skip over to this one. When your second derivative is negative, that means concave down. So the extrema is a max. What does your test tell you about when it's 0? This test fails. So that means we got it for that point. Go back to the first derivative test. So 2 out of 3 times it worked. Okay, so if it fails, here's what we do. We do a little mini first derivative test underneath of that. Okay, so if you remember, first derivative test, you do intervals, and we're going around the point 0. However, I'm not going from -infinity to 0 and 0 to infinity, because I've got these numbers that I already know something about. So we're going to go from -1 to 0 and 0 to 1. That's why I have you put them in order. So if you have to go back to the first derivative test, you already use those numbers that you have in there. Then we need a test value. So I'm going to pick -1/2 and 1/2. And we put those into the first derivative, which was this. -15x to the 4th plus 15x squared And we have to figure out when we put those numbers in if they're going to be positive or negative. So if I put a negative 1/2 in here, it's going to be 1/2 times 1/2 times 1/2 times 1/2. It's going to be negative 15 times 1/16 plus 15 times 1/4. Which one's bigger? Is this going to give us a bigger number, or is this going to give us a bigger number? It's going to be positive. When you put a 1/2 in, guess what? That doesn't change this because it squares it. It's going to be positive. If the first derivative is positive, what's that tell you about the original? Increasing. Increasing. If it's continually going up, is there a maximum in there? No. So this one failed, and then the first derivative test proved to us, yes, there is no extrema there. So our final answer is, we're going to write, it said find the extrema. So we want to write where the min and the max are. Okay, now remember, for extrema, your min and your max are the actual y values where they occur. So for our min, we're going to plug a negative 1 back into the original. And this will also catch it to see if it's really a point. If we plug a negative 1 in here, negative 2. Okay, so I'm going to go back down, write that in. The min is negative 2 when x equals negative 1. And then my max, I'm going to plug a 1 in there. What value do I get in the original when I plug a 1? 2. So my max is 2 when x equals 1. And there's my answer to that question. Okay, so that was our first run through. What do you want to talk about on that? If it says using the second derivative test in the directions, yes. And I will force you to use it on the quiz. Yeah, Nick. You are. That's exactly it. Yeah, that's perfect description on that. Any ideas on why the calculus book forces you to do this test? I have some ideas, but do you have any ideas? No. Why would we have this test? Any ideas? Okay, yeah, we can think about that. I like that. One thing they do, and this is when you get into higher math, they show you things that work simply because they're possible. And this is a test that it works. I mean, most of the time it works, but it's mathematically probable, so they show it to you. Another thing, it kind of brings concavity and extrema into one test. First derivative test tells you about mins and maxes. Test for concavity tells you about concave up, concave down. This tells you about both. This is your min and max. This is your concavity. So there's one good thing about it if you're searching for something. But the bad thing is sometimes it doesn't work and you've got to go back to first derivative test to check that out. Any questions on that one before we try another one? Mackenzie. Yeah. That is swing of height. Mm-hmm. All right, let's check out another one then. Let's do Let's use the function x to the 2/3 minus 3. We're going to find the extrema of this using the second derivative test. With a rational power going on in there. Okay, so first step is to find your critical numbers. So to do that, we derive this and set it equal to 0. Okay, so to derive x to the 2/3, bring your 2/3 down to the front, subtract 1 from the power. What is that? What is the derivative of -3? 0. So I don't need that. Okay, now I'm going to fix that negative exponent, and I've got this going on. So there's my first derivative, simplified. I want to know where this equals 0 and does not exist. So I'm going to set the top and the bottom equal to 0. When does 2 equal 0? Never, so that's not a critical point. Then to solve this, divide by 3, cube root, x equals 0. So we only have one critical number. It's x equals 0. Okay, now we're going to use that in our chart. I'm going to go ahead right now from here. I'm going to derive this again. And instead of doing the quotient rule, I'm going to derive from this point. Bring my -1/3 down. When I do 2/3 times -1/3, I get -2/9 x to the -4/3. And then I'm going to fix that and have -2 over 9 x to the 4/3. It's a little bit ugly, yes. Okay, now let's create our chart. It only has one critical number. So we're going to have critical number, sign of second derivative, and extrema. And that's why you want to make sure and know the titles for all of your tests, because I'll be looking at those, because there's 3 different tests. You need to know what each of them are for each of those 3. X equals 0 is our critical number. Plug that back into the second derivative. When you put a 0 into that, -2 over 9 x to the 4/3. Undefined. There's a 0 in the denominator. This test fails right from the beginning. Nothing salvageable right there. So that means we revert back to the first derivative test. When you put a 0 in here, 0 to the 4/3 times 9 is 0. So 0 on the bottom doesn't exist. And that's the only critical number. That is it. Okay, so second derivative test has not helped us at all. So we go to the first derivative test. We do our intervals up here. Do I need to make sure and bookend it with anything? Do I have other critical numbers to stop it? No. So this one I do go from -infinity to 0 and 0 to infinity. I'm going to pick -1 and 1. And we put these into the first derivative. Okay, so if I plug a -1 here, what is the cube root of a -1? -1 times 3 is -3, so 2 over -3 is a -3. When I plug a 1 in here, what does that give me? Positive or negative? Positive. Okay, so that tells me this first derivative test, if the first derivative is negative, the original is decreasing. If the first derivative is positive, the original is increasing. Is that an extrema right there where it switches? What kind? Min. So here, the second derivative test failed, but when we went back to the first derivative test, it helped us out. And so what we're going to do for our answer is a min. Okay, then you put 0 back in the original to figure out what the y value is. And that's going to be -3 when x equals 0. And there's our answer. On your quiz, pretty much expecting for at least one of them give you something that fails. So, you need to know all 3 tests for this quiz that's going to be coming on Friday. You got the test for concavity and the second derivative test that are part of this section. But if the second derivative fails, you got to go back to the first derivative. You have to know all 3 tests for this quiz that's coming on Friday. All right, we've got one more. We can do today or tomorrow. Do you want homework time today, or do you want to do another example today? Do another example? Okay. Tanner, did you say homework? Do we need to vote? You're feeling homework. Oh. Let's do a class vote. Example. Homework. Oh, example wins. Okay, let's do an example. G of x equals x squared times 6 minus x cubed. We're going to use the second derivative test to figure out where the extrema are. This one's a little more complicated. Can you tell why? Chain rule and product rule. And we get to derive it twice. Alright, so I'm going to jump into the first derivative. And it's overall a product rule. Within the product rule, we have a chain rule. Okay, so it is first times the derivative of the second. Don't forget that -1 as a derivative of the inside. That was my chain rule in there. First times the derivative of the second plus the second times the derivative of the first. Now remember, our goal is to take this and set it equal to 0. So we definitely want to do some simplifying. I'm going to make this, combine these 3 parts, and have -3x squared times 6 minus x squared, to join that together, plus 2x times 6 minus x cubed. Are you okay with that step? This, the derivative of the inside of this is -1. Question? Did I hear a question on that? Okay, now, these 2 terms, do they share anything in common? But they have a 6 minus x squared, something else. Let's just go with the x part, because one's a -3. Okay, so if we take that out of them, we'll get a -3x is all that's left for this, plus 2 times 6 minus x is what's left for that second one. And we'll make sure we're okay before we go any farther there. Okay, now I'm going to simplify inside those brackets. This is going to be -3x plus 12 minus 2x, which is going to simplify to this. Okay, now it looks kind of ugly, but we have 3 things that we want to set equal to 0. So this is actually a good spot to stop and find the critical number. Set this equal to 0, and we'll have all three parts equal to 0. Okay, so x equals 0 is one of my critical numbers. Square root this, so you're square rooting 0 and adding x. X equals 6 is another critical number. And then here I'm going to subtract 12 and divide by -5. So x equals 12 fifths is another one. Okay, are we okay there? If we're not okay there, I want to make sure we are. Anything you want to ask about that part? Let's be really loud in 3 seconds. No, just kidding. Okay. Now, we're got all this math going on. Do you remember what we need to do next? We're going to do our chart. Okay, so in our chart, we're going to have 3 critical numbers. So we've got and remember to put them in order. So if we have to go back to the first derivative test, we have our bookmarks. So we're going to go x equals 0, and then which one's bigger, 6 or 12 fifths? So that goes over here. X equals 12 fifths. Okay, now what's our next step? Second derivative, which we need to take. Okay, so we have to come up with our second derivative. I think you voted for this. You have different options on where you feel comfortable. I think I'm going to take my derivative at this point, as I think where it's going to be the cleanest. You could do a triple product rule here. You could do like product chain rules here. I'm going to do it from here. That's where I'm going to start. Okay, I'm going to actually bring that down so I have it to look at. So my first derivative all right, so what I've got is I've got these two things being added together. In each of those, I've got a product and a chain. 4 days without calculus was too much. We need this. All right. So the second derivative, looking at these two parts, the first times the derivative of the second. I think you voted for this too, Lane. Plus the second times the derivative of the first. That's halfway there. Get some numbers in there. What if all 3 of them fail in this chart? How will you feel? All right, then the second part, I've got these two things. Okay, so I'm going to go down here. Plus the first times the derivative of the second plus the second times the derivative of the first. Yeah. This is the first half of it. This is the second half of it. Okay, there are 4 terms. Do you see all 4 of them? 4 things that are ultimately being added. Well, yeah, let's factor some things out. What do they all share?
6.
Yep, okay. Any number that's in all of them?
3.
2. Okay. Okay, so out of this first one, if I take a 2 and a 6 minus x, that leaves me with 3x squared. No, because there was another negative 1 over there. Okay, then here, if I take one of those 6 minus x's out, and a 2 from here, it's going to be negative 3x times 6 minus x. This is from here, so I took one of my 6 minus x's out and took a 2 out of that. Okay, then here, take out one of my 6 minus x's and my 2, and I'll have minus 3x times 6 minus x plus 6 minus x squared. Be okay with that. I mean, we know what's going on, not if we're really okay with it. Okay, now, here's what you need to decide. What are we ultimately doing with the second derivative that we started a year ago? Karen's throwing her drink. We're plugging our critical numbers in. You decide where you want to simplify it to plug your critical number in. You want to stop at the yellow? One more? Okay. What do we want to do for this one more step? Those parts? Okay. So then we'll have 2 times 6 minus x. We'll have a 3x squared minus 18x plus 3x squared minus 18x plus 3x squared. Do you want to FOIL that? No? Okay. You want to combine that just because they're right there waiting to be combined? Okay, me too. Okay, so then we're going to have 9x squared minus 36x plus the quantity 6 minus x squared. You want to? We're running out of time, or else I would want to too. I want to make sure we finish though. Because it would be nice how it works out. The 36 is okay. Alright, now our critical numbers that we're plugging in here. Let's do a 0 first. Okay, so we've got 3 major parts. If we put a 0 here, it's plus. A 0 here is plus. Okay, a 0, 0, 0, 36 is a positive number. So when you have all those positives being multiplied, that's positive. Okay, let's go to 6 real quick. Okay, if we go to 6, if you plug a 6 in right here, what do you get? 0 times anything is? Alright, 12 fifths. We can do it. 12 fifths. No assumption rule. What are you assuming? There's a 0 in play. You sure? Alright, let's see. Let's check her out. 12 fifths is 2.4. It is. When you put a 2.4 in here. Okay. 2.4 squared times 9. Okay, you're thinking good. Minus 36 times 2.4. That's negative. plus, is that, did Aaron do math right? You think so? Alright, I did it. Alright, interpret. A positive second derivative means what kind of extrema? Negative means, what does zero mean? That's why we have that discussion. The second derivative test is possible, so that's why we learn it. You got to go back to the first derivative test.
Just for that one?
Just for 6.
Yeah.
It tells us about concavity.
Well, then why don't we do a concavity one in the first and
Well, then that's 2 tests too.
Alright. What's your goal
Your goal is for mins and maxes.
when you get min and max?
Okay.
What?
We got to figure out if this is a min or a max now.
Oh.
Okay, what are my intervals? Be careful. You got it. Okay, let's pick 3 and 7. Put them into the first derivative, because it's now the first derivative test. 3 into the first derivative, that's negative, positive. This is positive, positive. You want me to tell you? Plug a 7 in there. Positive, negative, 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 positive. Any min or max there? Well, then we would answer these two. We would plug those values in and get our y values. Oh my goodness, Bailey, you can't talk about it like that.